Okay, I'm going to go ahead and get started. My name is Douglas Wightman. I'm one of the engineers at Adaptive Computing. I work on the Moab core engine, the main scheduler. And I think there's two strikes going against this presentation already. First, it's after lunch. The lights are low. So that's definitely not going for me. And second, I'm coming off of a cold, so please have patience. And if you want to fall asleep, that's all right, because I think they're recording this for later. You can always catch it later. So the session today is on setting policies, SLAs. I'm breaking the discussion into two things, mainly three things that we're going to be talking about. The first one is on identity managers. So we're going to talk about what are identity managers in Moab, how can you use them, what's the format, what are their different tweaks and policies and best practices. Then from there, we're going to go into one of their most powerful capabilities, and that is importing a fairshare tree. So we'll talk about fairshare trees, how to use them, some of the lesser known features and knobs and things like that. And then after that discussion on identity managers and fairshare trees, we're going to go off on a completely different subject and talk about dividing the cluster, what it means to divide a cluster, the different ways that you can do it, hard division, soft division, all that kind of stuff. So let's dive into identity managers. Moab identity managers are useful to gather information about users, groups, accounts, classes, QoSs, the five main Moab credential types, from an external source and pull it into Moab. So this external information can include things like access, who has access to what account, who has access to which QoS, and also policy information like limits and priority and fair share, partition access, all that kind of stuff can be imported dynamically from an identity manager. The reason that we recommend going with identity managers is because they can be manual or dynamic. You can change the settings inside of the identity manager, and you don't have to restart Moab to get the policies to take effect. Moab will either read the identity manager at regular intervals and update its information, no restart required, or you can even call out to a specific command in Moab to tell Moab to go out and refresh the information from the identity manager. So it's a way to change policies on the fly, to tweak these things without having to restart Moab at all. So configuring an identity manager is pretty simple. It goes inside the Moab configuration file. And at that point, there's really one of two. It's going to be a file or a flat text that Moab is just going to read that file, or it can be an executable that executes something on the system that pulls in information. At that point, you set the refresh period. If you want one, you can set it to infinity, and then it never refreshes, and you can just do it manually from the command line. Or you can tell Moab to go out and query that file or query that script once an hour, once a day, once a week. And then Moab will pull that information in without restarting, update its internal counters and variables, and continue scheduling. So what goes in an identity manager? As I mentioned before, you've got access information, you've got policy information. It's a very simple format. You just do the cred type, user, group, account, class, QoS, colon, the credential ID, so the name, and then you just do a whole bunch of adder equals values, whatever it is that you want to specify there, where adder is going to be something like a list. That's account list. Or email address, fair share target, max job, max mem, max node, plist, priority, qlist, qdef, all these different policies that you normally would put inside the Moab configuration file, you can put inside of the identity manager, and then Moab will read that in, update it on the fly, change it however you'd like. It's pretty simple. So these are some examples. So the first example, we've got 4 groups, and we're setting a fair share target on each of them. But then we're also setting an account list, or a list, on one of them. We're setting something like an admin level on a user, and then max node and max job, and it does support hard and soft policies. The next example is a little more interesting. So there, we're doing user default, so we're setting a default user, and we're saying, as I mentioned before, you can put limits in here. So here we're going to say max gres GPU equals 2. So that means every user on the system gets can use a maximum of 2 GPUs at a time. You can do multi-dimensional policies like the max job per user. So they have class batch. Max job per user equals 10. So from there, every job in class batch, every user that submits to class batch gets up to 10 jobs that can be active at any given time. And then the same for high prio, just set it to 20. So you can set normal limits like max job, like the example that's here. Just normal limits, max node and max job. You can do multi-dimensional limits, and you can do gres limits. You can all do these. And then again, if you decide to change these, Moab will just read it while it's running, update its information on the fly. And then the bottom one is another example of access or credential access. So here, it's giving users access to different accounts and QoSs, setting ADEF, A-list, QDEF, QList, and things like that. I should mention that for things like the access list and account defaults, this will affect, once the change goes in place, it will affect new jobs that are submitted after the change. So Moab doesn't go through and remap all the jobs that are currently running on the system. Instead, it just affects new jobs that are submitted if a change is detected while Moab is running. Any questions so far? Okay, so that's basically the gist of identity managers. It's a very simple concept. It's just a way to pull in this information from an external source so that Moab can update it on the fly. It tends to be easier than maintaining, depending on site policies, it tends to be easier than maintaining just one master moab.cfg file. Instead, you can put these kinds of policies in a separate file that is updated dynamically. So really, most of the credential policies, like throttling policies and fair share and priority, they can all be set from within the identity manager. Yes?
So if you're changing the fair share target,
Yeah.
so let's say that you're drastically reducing someone's fair share from what it had before.
Uh-huh.
So does it reset the time period that it's looking at, or are we still looking at the same rolling time period?
Yes, it's still looking at the same rolling time period. So if you were to go in and drastically reduce somebody's fair share target, the immediate effect would be that the user's idle jobs in the queue would drop in priority.
Right now in our configuration file, we do something like this, but we include, hash include and file name at the end of it.
Yes, uh-huh.
So where is it different?
If you do an include file in the moab.cfg, Moab does not refresh its moab.cfg file every so often while it's running. In order to get a refresh, you have to restart Moab. So that's the main difference, is that you can put it somewhere and then Moab will refresh it periodically. Yes?
Is this valid in 6 or is this a 7?
Oh, this has been in since 5. It's been in for a very long time. Okay, so were there any other questions on identity management? Yes?
Our experience with Identity Manager when we ran it was that it seemed to be only additive. That, for example, you could add a new user, or you could add a throttling policy.
Uh-huh.
But if you then took it out of the Identity Manager, when it reread it, it didn't take out that policy.
It depends on the policy. So you are right. It depends on the policy. Now, if you were to go in and you wanted to change the max job and get rid of it, well, then you'd set it to -1. You wouldn't delete it from the file. You'd set it to -1. -1 means no limit. So for something like a limit, like max job or max node, you'd go in and set it to -1. For something like an A list, you can tell Moab, there's a cred reset list that you can tell Moab, okay, when I change an ADEF change, that makes sense. There's no additive property to an ADEF, but to an A list there is a property to add it. So you can tell Moab to reset it whenever it queries, and then you won't get the additive behavior that you're seeing. But you're right, by default that is the behavior for certain things. Okay, so moving right along with identity managers, we're now going to talk about fairshare trees. The reason that I include these two together is because there are two ways of doing fairshare trees. One of them is in the moab.cfg file, and one of them is in the using XML inside of the identity manager. For sites that have tried one or the other, they usually learn very quickly that doing it inside of the moab.cfg file becomes quite a burden. There's a lot of configuration that goes in there, and it can really make a mess of your moab.cfg file. So for that reason, I'm including the way to do it via an XML tree inside the identity manager. So the sites that we have used doing large fairshare trees, extremely large fairshare trees on the order of thousands of users, they will use an identity manager to do it, as it becomes much more manageable when they do it that way than if they were to try that in the Moab configuration file. So what is a fairshare tree? Just a quick background on fairshare, just in case somebody doesn't know what it is. Fairshare is a way to say that what past usage history is how it affects the priority of my current jobs. So in other words, if I used up the whole system yesterday, I'm not going to get to today. Another way of saying that is the more I used in the past might mean the less I can use now, or the less I used in the past, the more I can use now. So it takes into account the past historical usage in prioritizing the queue of idle jobs now or today. So in a lot of cases, you'll have a fair share setup where you will say, I want this user to have a fair share target of 10. What that basically means is 10% of the system. So as long as that user is using less than 10% of the system, his jobs are not going to be penalized in priority. But as soon as he goes above 10% of the system, the priority of his idle jobs starts dropping. So a fair share tree is a way of doing something like that, but with a lot more arbitrary mappings and groupings for these users. So here's an example of a fair share tree. We have the top of the tree, root, and then we basically have three accounts on the system. Account 1, Account 2, and Account 3. And then we have groups, Group 1, 2, and 3. And you can see that Group 1 and 2 are allowed in Account 1 and 2, and Group 3 is only in Account 3. And then we have three users on the system, User 1, 2, and 3. And again, User 1s are over there, and User 3, and User 1 is also in Account 3 based on the way that he submitted the job. So what this does is this keeps track of usage in a hierarchical fashion. So in other words, it keeps track of the usage of jobs of a certain account, of a certain group, of a certain user, instead of just grouping all usage from a user, no matter which account he was running it in, under one credential, that user. So it allows for some very rich policies when it comes to setting fair share. For example, let's dive in and look at this example with actual numbers. It makes sense. It makes sense conceptually to have these rows add up to 100, just because we tend to think is 100%. They don't have to add up to 100, but for the purposes of this, I am having them add up to 100. It makes it easier to understand. So for this, we have 70, 20, and 10. So this branch of the tree should get 70% of the usage on the system. If it goes over that, the jobs start being penalized. If it's under that, the jobs are just fine. This branch should receive 20, and this branch should receive 10. And then within that, we have another split out. So this group should receive 30% of the usage of the 70%. So 30% of 70%. And going down, you get this user should consume 50% of 30% of 70% of the system. So it allows for some very rich type policies to say who should get usage of the system. What is fair for your site on the system? You may have a setup where multiple accounts, and one is a high priority account, or even a class or a queue. You may have a high priority queue and a low priority queue. And the high priority queue, you want to distinguish the usage of the high priority queue for a given user over the usage of the low priority queue for that same user. So this allows you to set that up so that if you have different targets for each one. I'm not exactly sure what you'd have it. Maybe you have a very low target on the high priority because you don't want it consuming the system, and a very high target on the low priority because it's okay. It's going to have a lower priority. So however you want to map it, this allows you to tweak those settings. So as I mentioned, the usage is done from the leaf nodes to the parent nodes. That's the way the usage is calculated. It allows arbitrary credential mappings. Moab, when it gets a job and it's going to decide, well, where in this tree does this job go? It does a depth first search. So it will go down the tree starting, and because this is defined with XML, the order is defined within the XML, and so it will do a depth first search to try and find a location for the job. The way that this works is going back up to this, where we have accounts, groups, and users. So let's say a new job enters the system, and we need to decide, okay, where does this job fall in the tree? Where is its usage going to be accounting? So the first thing it does is it comes down here, and it says, is the job's account 1? If it is, then it keeps going. It says, is the group 1? If it is, then it keeps going. If it doesn't, then it comes back up. So the first place that it finds where it's gone the full depth and there were no violations or no mismatches, then that's where the job is going to reside. That's where the usage is going to be accounted for. So in effect, by not putting any other users under group 2, that means all users will match group 2. So Moab does this depth first search when it's trying to find where to put the job. And by default, if Moab can't find a place to put the job in the tree, it'll still run the job. You can change that by setting fstree as required. So that says if Moab can't find a location for the job in the tree, then the job's going to go on hold. Moab's not going to run the job. And when you run check job, you'll see a message, cannot find a location in the tree for this job. You can go one further and say that the fstree user is required. And that means that I actually have to find the user of the job somewhere in the tree. So if you were doing that kind of a policy, then you would need to specify all your users in the leaf nodes of the system. But that way there's no ambiguity as to where the job is going to end up, because it will end up where the user is. Finally, yes, go ahead.
What happens in the case when the user is, for example, a member of more than one account or group?
Well, a job can only have one account, and it can only have one group. Yeah. Exactly. That's exactly right. So the fstree ACL policy is just kind of this shortcut that says, if in my fairshare tree I've stated that user 2 is part of account 1, I don't need to put that anywhere else. Moab's going to go ahead and let user 1 and user 2 into account 1. You can turn that off. I'm not sure why, but you could turn that off if you wanted to with the fstree ACL policy. Are there any questions so far on fair share trees? Yes?
So by default, let's say like we don't have any of these parameters in the configuration file. So historical usage, Moab considers by default, right?
So you don't have a fair share tree. Oh, so you don't have any of these? Yeah, so if the job finds a place in the tree, great. Then that's where Moab's going to do all of its accounting. When the job finishes, it's going to update that part of the tree's usage on the system. If a job can't find a place in the tree, well, there's nowhere to update when it's done. So the usage, if you had it accounted for somewhere else in just generic fair share policies, it would still be accounted for there. Yes?
You mentioned that jobs can only have one user and one group.
Yes.
And they also only have one account.
Yes. One account, one class, one QoS. It's just one for every job. Okay. One other thing that fair share trees also support are limits. You can put a limit on a node in the tree. You can set max proc, max job, max PS, all the regular limits that you would specify. Now, at first this seems kind of simple, but when you think about it, you realize that this is actually a very powerful policy right here. If you've defined a tree for all the users and the groups on the system, you've enabled basically arbitrary depth, arbitrary dimensional policies. So, for example, right now in Moab, you can go into the configuration file and you could do a class CFG batch. Max job per user equals 10. Kind of like the example I showed earlier. And that says that every user in this class gets 10 jobs. But what if you wanted to say every user in this class, in this account gets 10. So now you're actually going 3 dimensions. Well, that can be done with a fair share tree. So with this setting, it's saying that the maximum job for this user in this group, in this account, is 12. Meanwhile, if he runs over here, he doesn't have that limit. So you can set arbitrary dimensional limits on users that are updated dynamically while Moab is running to allow for some very, very rich policies if you would want to set them. And again, you can do hard and soft limits here as well. So those are supported in the tree.
What's the syntax for this?
Let's take a look. That's the next slide. So it's defined with XML. It's imported from the identity manager, and the general format is to define the T node in XML, and you say the type of the credential, account, user, class, group, and then the name, then the share, and then any other kind of limits. So that tree that I had as an example, this is the corresponding XML for that tree. And you can see that with XML, because I indented it, but you can indent it. But because of that, it's a lot easier to visualize the tree using a language like XML than it is with the Moab CFG, which is why I didn't include the Moab.cfg. It's just ugly. I don't like it. Don't use it. If you can, avoid it. Okay, so here we're setting, we set the name is group 1, the type is group, the share, and the limits right there. And you can specify more than one limit. It's just space delimited, so you do max PS equals 9,000 space, max job equals 12, and you can put whatever limits you wanted to right there. And so this is that exact tree, and this is what the corresponding XML looks like.
Would you use more than one limit statement, or would you use space?
No, you would put it in the same. I think it would probably support both. I haven't tried it. I've only put it in one limit statement with multiple in there. But space, just a space. But knowing the code, just doing a mental check in my mind, it would work if you did multiple limits as well. If you just said limits equals, limits equals, limits equals. They would most likely both work. But follow what's in the docs. Exactly. Okay, so that is what the XML looks like. And this would just be... We've got this syntax. That's some identity manager voodoo magic. You could just copy and paste that. But this is basically everything that's in the identity manager. This is what you would put in the identity manager. And you can mix it with the other contents of the identity manager. So you could do the regular mappings at the top and then have the tree at the bottom, or vice versa. It's all right there inside the identity manager. And because it's part of the identity manager, you can change it on the fly. Moab will update itself, and it will go through and change all the map. Yes?
How often is Moab looking for updates to this?
That was the refresh period. So you set it to either an hour, a day, or there's a command that you can run to tell Moab, go refresh right now.
And I assume that you use this independently from the Moab account manager?
Yeah. So this is a way to change the scheduling behavior of the priority of the jobs in the queue and the limits that are on the jobs, but it doesn't have to do with what a job gets charged at the end.
Okay.
Yeah. So you can use them at the same time. Because allocation manager actually doesn't change how jobs are prioritized. And that's what this does. That's a good question. Okay, so once you've got a tree like that in the system, you can run the mdiag-f-v and get the output, and this is what that same tree looks like when you run that command. So you can see the targets. Right now, I ran it on a system that didn't have any usage, but normally you get usage in there. And then you'll see these numbers here. This is basically the priority, the fairshare tree component priority of the job. So if you were to run the mdiag-p command, this is the number you would see in the fairshare column. And then you've got max PS and all the limits that you also set as well. And it looks like some of my math was wrong in that tree. So these ones didn't add up to 100. But again, that's not required. They don't have to add up to 100. That's just a way to conceptualize it a little bit better. It does. It makes it a lot easier. Otherwise, yeah, I mean, we've had some who go in and they're just picking arbitrary numbers in there, and then they're like, "Where do these numbers come from?" And it's like, let's simplify it down a bit, and it makes it a lot easier to understand. Okay. So, any other questions on fair share trees? Okay, let's dive into dividing the cluster. Dividing the cluster is something that we see pretty much every single one of our customers do. It's just a natural thing that happens on any cluster or grid. And the reasons for dividing the cluster can be ownership. So you have some group that purchased a set of nodes. They want the system admins to take care of them, but they want preferential access on those nodes. Or you may just have politics at a site. You may have some groups that want certain access and other groups that want others, and they fight amongst themselves and then tell you what it is that they want, and you go and implement it. You can also have just application affinity. So you may have software that's installed on one machine and not on another, and so that's a natural division of the system. Not every node is the same. You can have network divisions, whether it's a subnet or a VLAN or something like that. That's another way, and that goes along with all other hardware type divisions. So you may have large memory, you may have small memory, you may have different OS stacks on some machines or others. Just the natural inclination of any system is to just get more and more complex as it keeps going, and so things get divided up. It's the law of entropy. I guess it applies to clusters as well. So the best practice when you're trying to decide how to divide a cluster is to keep it as simple as possible, obviously. Don't introduce more than you need to introduce. While some things might be nice for admins, they're really confusing to end users, and vice versa. So too much division leads to inefficiencies. By that I mean that you may block off a certain set of nodes for a certain group, but then those nodes hardly go used, and so lots of other inefficiencies on the system. So let's talk about the ways to divide a cluster and the reasons to use the different types of cluster divisioning mechanisms and theories inside of Moab. We have the hard division and we have soft division. Hard division, the way I think of it, the way that most sites I think tend to think of it, is the job cannot span. If the job were to try to span, it would fail miserably, whether that's because of a network boundary, so you've put a job over on node A and node X can't even reach it on the network. If you were to try to span it, the job would just fail. So that would be a hard division in the cluster. There's just no way that a job can span that. It can be hardware boundaries, network boundaries. You can have memory boundaries, things like that. So the three things that I categorize as hard division type ways to divide a cluster would be partitions, classes and queues, and node sets. And you'll notice that node sets is on both sides. That's because you can configure node sets to be hard or soft. It's up to the site if you want to configure node sets to be hard or soft. So that's why it's on both sides. And then a soft division tends to be more of the political boundaries. So that means a job is welcome to span across. It won't fail if it spans across, but we don't want it to span across boundaries. So those would include things like reservations and node sets, if you so define node sets to not be a hard division. So let's talk about partitions. Most clusters only have a single partition. And why is that? Because a job can span the entire cluster on most sites. So there's no reason to partition off the cluster. However, especially in the case of grid, a job cannot span the entire system. A job has to run within a particular cluster on a grid. So the way that Moab works by default, if you have Moab talking to multiple resource managers, maybe it's talking to 2 torques, maybe it's talking to 2 slurms, or a torque and a slurm, or 3 or 4, then Moab knows that a job cannot span from one torque system to another torque system. And by that I mean across 2 different PBS servers. So it creates a partition for each resource manager in the system. It also does that in a grid. If you have one Moab communicating with another Moab, a job cannot span across multiple Moabs, so Moab creates a partition for every resource manager in the system. Excuse me. This can also be because of network topology, and that usually also means a grid configuration where you have nodes that just, in one section of the system, that cannot communicate with nodes on another section of the system. So a network topology might be another reason to use partitions on the system. Other than that, there tend to not be very many reasons to use a partition. A partition, as I mentioned, it's a hard boundary. So if you don't have that hard boundary, maybe you don't need to use partitions. But if you do have the hard boundary, because you have legitimate reasons to have those hard boundaries, network, grid, whatever, partitions can actually be very useful. So here I wanted to talk about some of their lesser known qualities. Because a node cannot belong to more than one partition at a time, you can start doing some interesting things with partition. We have some sites who turn on this parameter called per partition scheduling. Per partition scheduling tells Moab to basically reorder the queue using a different policy set for every partition in the system. So we have some sites who are doing grid configurations, and they have multiple clusters running under a single Moab. But what they want is they want user A to have a higher priority when he runs on partition or when his job is evaluated on cluster A. But when that same job is evaluated on cluster B, that job should have a much lower priority. There's another group that has a higher priority. So by turning on per partition scheduling and setting a config file for each partition, you can set up different things like credential priorities. You can set up actually even different fairshare trees for each partition in the system if you wanted to. Then what happens is when Moab schedules jobs, it goes to the first partition in the system, and it will prioritize the jobs and schedule the jobs there. Then, when it's done, it will move on to the next partition, reprioritize the jobs using the policies of that partition, and schedule the jobs there. Now, Moab is a start time scheduler. It is not a completion time scheduler. So what that means is, if a job can start now, that is the holy grail for Moab. Start that job. It can start now, start it. It's not looking at where the job is going to finish the soonest. It's looking at where the job can start the soonest. Now, there are some R&D projects going on as far as completion time scheduling, because it's a different type of scheduling, and it definitely has its applications, especially in grid. But currently, Moab is a start time scheduler. So each partition has unique policies. Each partition can have a unique fair share tree. You can have different max job limits and max node limits in each partition. So really, it's almost like you're getting a completely different scheduling experience across each partition in the system. Then a job that comes into the system, you can either, that job can request certain partitions, it can be open to all partitions, or as an admin, you can say jobs from this group have to go to this partition, and jobs from this group have to go to this partition. And you can use job templates as well to stick partition requirements on the job. So that's partitions. Classes and queues. This is something most people are already familiar with, so I'm not really going to dive into heavily. I just want to mention one of the capabilities of Moab and one of the gotchas that we've had come up. So by default, if you're just doing Moab and Torque and you're not changing any kind of configuration, the way that Moab and Torque and Slurm all work together is that a class is available, a class that's defined in Torque, or a queue. Classes and queues are the same thing. A queue that's defined in Torque is available on every node in the system. Now let's say you want to change that. You want to make it so that this class is only available on a subset of the nodes. Well, you can do that using the host list. And I tend to always use the R colon rather than the X colon, because it tends to make more sense. X is an exact regular expression. R, it's a range. So here I'm doing a range, and I'm saying class batch is going to be on nodes 0 through 299. Express is going to be on 300 through 449. Serial is going to be on 450 to 499. And then you'll notice this fourth class, fast. And I haven't defined a host list. So where is that class? It's everywhere. That's right. We've had some customers who, because they put a class, like let's look at class batch. They say class batch is on nodes 0 through 299. Sometimes they thought that would exclude every other class. But that's not the way it works. The host list is only constricting the class that you put it on. So if you want to have this division across all the classes on the system, you'll need to define a host list for every class on the system to define where it goes. Okay, so those are the two main hard divisions. We're going to dive into the first one, reservations, and then we'll talk about node sets. So reservations, as we all know, they're very flexible. They're dynamic. You can tell Moab, I want 10 nodes. If one of them goes down, Moab will search for another one. They can be one time. They can be persistent. I'm not going to dive too deep into reservations right now. You can do things like rollback reservations, owner preempt, things like that. I will talk about some of the gotchas with using reservations. So because reservations are so flexible, that gives you a lot of rope to hang yourself with. So be very careful with reservations. If you're going to use reservations to divide up your system, I definitely recommend that you put host lists on the reservations rather than doing just task count based reservations, the ones that float around. Just because if you have to do the floating around ones and you have to divide up the whole system with floating around type reservations, we will work with you. But we will probably have to work together. But we will work with you to get it to work. Another thing to think about with reservations is that because they are very dynamic and they move around and they require actually more processing by Moab than the other types of divisions. Partitions and classes, though, those are very cheap as far as scheduling goes. Reservations are definitely on the more expensive side. So keep that in mind if you're running tens of thousands of jobs through the system. Or have lots of nodes, that's right, if you're scaling in either one of those directions. So now let's dive into node sets. Node sets can be soft partitions. Yes. Yeah. Yeah. Yes. That's a lot of processing. It would be a lot of processing. So there's not really any kind of limit in there. Most likely what you would see if you put in lots of reservations and you had lots of nodes, lots of jobs, is you start to see your check jobs time out. Because Moab's busy. It's busy scheduling. So that's really that's what you see as an end result. Start seeing some of Moab commands time out. So reservations definitely have their place on every system. Don't get me wrong. Reservations are very powerful, very useful. They should be used. They have their use. But I wouldn't use them if I were dividing up the entire cluster. That's not why I would use them. I would use them more for one-time uses, or if you know that you want this particular queue to have access at night or something like that.
Essentially, just as a
Yeah.
what you're saying is almost the opposite of what's been in the documentation for a long time. Just so you know.
Well, that's why you come to Moabcon, right?
The documentation actually, maybe it's changed recently, but for a long time it actually gives you the impression that partitions were deprecated
And
in a way.
no, partitions are not deprecated. In fact, there's even more things that we're planning around partitions. Because partitions don't overlap nodes, from a scheduling perspective, there's a lot of interesting things you can do there. For example, we could thread off the scheduling of each partition into a separate thread, and then that way you could get a lot more throughput through the system. There's a lot of cool things you can do with partitions that you can't do with other things because they're rigid. So yeah, partitions are not deprecated in any way. And neither are node sets. Node sets, if anything, are getting a lot more attention now, and we're actually putting in some more policies that will be coming out with the next HPC release of Moab around node sets. But for now, we'll talk about what they can do right now. So a node set is a set of nodes. That's why we call it a node set. Node sets can overlap with each other, and they are around features. So if you were to try and visualize your cluster and put a tag on all the nodes that have features, the corresponding tags, then that becomes your node sets on the system. And now you can tell Moab to schedule using these sets of nodes. So conceptually, the idea behind node sets is this. If I'm asking, if a user is submitting a job saying the following, I want my job to run in one of these types of nodes, but I don't care which one. Just pick one for me. That's what a node set is for. So, for example, if you have different racks on the system, let's just start with racks, and a user says, I want my job to run within a rack. I don't care which one, but I want it to run within a rack because that's where the switch is, and they get a lot faster network communication. So that would be an example of a node set. So the first thing you do is you set the node set policy. That's usually one of. You just want one of the node sets. You set the node attribute to feature, and then you set the node set list, and that's the actual features. You may have some features that you don't want to be part of node sets, and that's what the node set list is for. You put in there the features that you want considered. And it can also be specified on a per job basis. A user can come in and specify his own node set requirement. But Moab evaluates node sets in the order that they were specified. So this actually allows for some interesting network topology type scheduling behaviors. In this example, I've got 16 blades, and each 4 is grouped into a quad unit, and then the 8s are grouped into an octet unit. For a job to run ideally, it should run within a single blade. However, if it can't run within a single blade, it should run within a single quad unit. If it can't run within a single quad unit, it should run within a single octet unit. And finally, if it can't do that, we'll just run it anywhere. So by specifying a node set list in the order of smallest to largest, starting with the blades, going to the quads, and finally the octets, that's the exact behavior that you get. Moab will now schedule these, and it will try to put the job within the smallest node set that it can. The first one that it finds that it can run in, that's the one that it will use. So therefore, jobs will try to run within the smallest, in this case, let's say it was a switch. Jobs is going to try to run within one switch. It's not going to try and span switches. And we call that nested node sets. It's really not a new concept. It's just a way of specifying lots of these and getting that kind of a behavior. The last slide, we're over. I just want to mention these two things really quickly. Delay and span evenly. We've had requests to have Moab say the following. A job comes into the system and it wants to run within a node set, obviously, because running in a node set means the job runs faster. But let's say a node set isn't available, and because Moab's looking into the future, that node set's not going to, or a node set is not going to become available for 2 hours. Well, what should Moab do? Is it worth it to the job to wait 2 hours for a node set? If this is a 2-week-long job, and running within a node set reduces the wall time of that job by a few days, then yes, it makes sense to wait 2 hours in order to get Moab to run that job within a node set. So that is what delay does. With delay, you tell Moab how long it is acceptable to wait for a node set. If Moab can't find a node set within that delay, then it gives up and it just puts the job anywhere. But if you want Moab to do that, then you can use, if you don't want Moab to do that, you can specify a delay of 99 days or something like that. And then basically you're going to wait for a node set. It's worth it to you to wait for a node set rather than to run anywhere. The last one is just a corner case. It's called span evenly. This just allows you to say, if I'm going to span a node set, I want to span it evenly. So if I have a 32 processor job, I want to first try and get all 32 processors within one node set. If I can't get them within one, then I want 16 in 2. If I can't get 16 in 2, then I want 8 in 4. So it's kind of it's the same kind of thing with delay, because you can specify a delay, but you get this different behavior to just say, I want to span evenly across the node sets. So in closing, there are certain things that require extra computation for Moab and certain things that don't. Reservations are the most costly because they also, not only do they have a space element, that is where they are on the system, they also have a time element, which means I'm on the system, but I'm only on the system from this time to this time. So that requires extra computation from Moab. Things like classes and partitions, those are the cheapest. Classes and partitions are very cheap as far as the scheduling. So if you've got hundreds of thousands of jobs going through the system, the most computationally effective way to do something like that is with a partition or a class. Yeah. So that's it. Thanks for coming. If you have any questions, feel free to come up and ask me. Thanks for coming.